Welcome everybody to the Random Interaction Seminar Series. Today we have Darshan Joshi from Harvard University who will talk to us about failed superconductor in a model with random interaction. Darshan did his PhD from St. Louis, is that right, Darshan?
No, TU Dresden.
TU Dresden, okay. And then, okay, so he was Matthias White, I believe, right? Yeah, and now he's working with Subir Sachdev and others at Harvard as a postdoc. So let's get it over to Darshan. So Darshan, it's up to you.
Yeah.
You can start.
Yeah, thanks for the invitation to this seminar, and thanks everyone for showing up despite this pandemic and a lot of speaking in Mumbai. So today I'm going to talk about recently interesting phase of matter, which is a critical phase. It's called a failed superconductor. You can also call it as an anomalous metal. And I will be studying this model and presenting a model using random interactions, which recently I have been interested in, which are inspired by the recent developments in Sachdev-Ye-Kitaev models. So let me start with my collaborator. So this is Chinwan Lee, who is a graduate student here, and Subir Sachdev, and the reference is here. So to start with the very basic, we all know about superconductivity. So essentially, this is the curve of resistance versus temperature. And for a typical BCS superconductor, you lower the temperature and the resistance goes to 0 at some point and it becomes superconducting. Whereas for a normal metal, you would have a residual resistivity, meaning that even in the T going to 0 limit, there is a finite value of resistance. And this is how you would distinguish a normal metal from a superconductor. And apart from just this thermal phase transition, which is as a function of temperature, you can also have a quantum phase transition, meaning T equals 0 phase transition, which is not driven by temperature, but let's say a magnetic field. So let's say schematically, you have temperature here on the y-axis, magnetic field on the x-axis, and you have some superconducting material, let's say, and this superconducting phase could be either destroyed if you increase temperature and go above Tc, or at T equals 0, you can increase magnetic field beyond some critical value and you can become, again, a normal metal. Similarly, you can also have some interaction-driven superconductivity to normal metal phase transition. So for instance, if there is let's say, an attractive Hubbard model at a theoretical level, then because of attractive interactions, you can have a superconductor even at T equals 0. And if you now increase your interactions and make it repulsive, then you will go to a Fermi liquid normal metal. So again, you have a scenario where you have a quantum phase transition between a superconductor and a normal metal. And typically, given the theoretical progress in superconductivity, so far, nothing really surprising or exotic seems to happen in such quantum phase transition between the superconductor and a Fermi liquid metal. These are all well-behaved phase transitions, at least in the models that have been studied so far, and you get just normal Fermi liquid kind of instabilities and so on, and Landau kind of phase transitions. But there are actually some two-dimensional materials where something interesting happens. And let me just show you some experimental plots, which were the motivation for our work. So these materials basically observed something anomalous. And this is a metallic phase, which is characterized by the property that it has a very low resistivity at low temperatures, but it's not as it doesn't become superconducting. So its resistivity is not 0, it's some constant, but it's much lower than what you would expect for a normal metal. So let me just walk you through these plots. So for instance, in this experiment, it's on this TA films. This is resistivity versus temperature, and different curves are for different values of magnetic field. So at 0 field, you can see it's a superconducting transition, and at Tc, the film becomes superconducting. Now you increase the magnetic field, what you see is that the resistance decreases very sharply, and it seems that it would become a superconductor, but it doesn't, and the resistivity simply saturates at some finite value. And this happens now if you keep increasing the magnetic field, the value of this resistivity keeps increasing, but it's still much lower than, let's say, the normal phase value, which is somewhere here. Similarly, in this second example, it's basically a similar experiment where you have resistivity versus the temperature, or here in this case, inverse temperature, for two different films. And you again see that there is this saturation behavior at a very low value of resistivity. And this can happen actually not just as a function of magnetic field, but some other parameters. So just to give you another example, here are two more examples where the tuning parameter is the gate voltage in these two-dimensional materials instead of magnetic field. So again, for some typical value of gate voltage, you have some superconductivity. So again, here, the y-axis is resistance, x-axis is inverse temperature. So you have some superconductivity, then you increase the gate voltage and you go to some metallic phase. So there is some residual resistance, but it's much lower again compared to a Fermi liquid metal or normal metal that you would expect. Similarly, this is another example on an array of niobium on gold substrates. So essentially, what the picture that we have, or what we expect for these two-dimensional disordered materials or superconducting materials, is that you have some superconducting phase, and it can have this thermal phase transition where about TC it's a normal metal. But now if you tune some non-thermal parameter, let's say like a gate voltage or interactions or magnetic field, you seem to go to some anomalous phase, anomalous metal phase, before you go into a normal metal. And this phase is what I call a failed superconductor. And the reason for...
Darshan, there was a question from
Sure.
one of the students, I guess. Unmesh, you can ask.
Yeah.
So,
sorry, I can't see the chat.
no, that's fine. That's why I'm looking at the set. You don't have to.
Yeah. So I was asking that what will be some actual numbers of the saturated resistance that you showed these plots of? The typical numbers of resistance, what will be?
So you can see from this plot, so it's how so it depends on the material. So for example, for this WT2 material, the resistance is like 10 ohms or something. Whereas for certain other examples, it can be much lower. It's like 1 kilo, much higher, 1 kilo ohm. So what is interesting here is, rather than the absolute value of this saturation, you should compare the ratio of the saturated value to the normal one. And it seems to be like, in certain cases, it can be as high as like an order of magnitude or 2 orders of magnitude higher. So here it's like a ratio of 3 or 4. But for instance, in this case, the ratio is like 1,000, right? I mean, here it's of the order of 1, here it's of order of 1,000. So it's like 3 orders of magnitude. So it really depends. And that's really something very surprising, that there's a very drastic change, very high conductivity, but not yet superconducting.
Okay.
And Darshan, just one more question which I had. There was some reports from maybe Abhay Pashupati and others that, there was some extrinsic noise which was giving you a finite resistance, and when they put, filters, everything went back to superconducting. And there was a bit of controversy about whether the failed metal is really there, or it is just an artifact of, how people are measuring.
Right.
So do you have any comments on that?
I have probably a very naive comment on this. I mean, so I'm aware of this, and it's true that these are very complicated experiments, and there could be some subtle heating effects and some substrate effects or connection effects and so on. But as far as I know, I mean, I'm taking a word from the experimentalist on this now, which I also learned from this review article that I cite here, that at least in these experiments, people have carefully checked the effects of heating and like the connections and so on. And they are quite sure that this is really the true effect. And recently, we also had talks from Aaron Kapitulnik, who was visiting here, and he also showed some new data on these critical phases, which I don't show here right now. But yeah, he had some recent experiments again on this anomalous metal, and it seems to be there ubiquitously in these, despite different checks.
Okay.
Yeah, but still, there could be some other experimental tricks.
No, because I remember this paper by Abhay Pashupati and others, where they put some noise filters, and then this went away and became superconducting. And basically saying that this was some external noise which was giving rise to the finite resistance.
Yeah, could be. So maybe maybe in those particular materials it could be the case,
Yeah,
but
sure.
at least in these ones it seems to be there.
Okay. Yeah, fine.
So Darshan, I had a question. So I know the importance of the 2 dimensions here. So I can see in monolayer WTE2 and things like that. But if I look at these experiments with array of niobium on gold, in what sense are they 2-dimensional? In the sense that they're films, but where does the dimensionality? Are they really at the limit of 2 dimensions for these films, like gold films?
Yeah, I agree. So it's slightly loosely put that it's 2-dimensional. I would say let's call it granular materials to be more precise, because these are basically some islands of this niobium puddles on some gold substrate or something. So you could also probably call it like a connection between small islands or something. And then maybe in this particular case, in fact, you cannot actually let's say call it like a purely 2-dimensional system. I agree with that. But here I just use the word 2D materials in a more general scenario, that there is a 2D substrate and you just put some islands, and even that is like 2-dimensional.
Okay. All right. Yeah.
Yeah. But as you will see that actually the model that I consider, it doesn't take into account actually the dimensionality being 2-dimensional. And that's also the surprising fact that why we could still get an anomalous phase, and I'll get to that. So at least the model that I use doesn't strictly actually use that.
So I'm relatively new to this. So you're saying experiments are motivated by these 2D, or let's call them kind of 2D systems, experimental results, but the physics is dimensionality independent. Is that maybe dimensionality independent? Is that what you're?
Yeah, I think so. Yeah.
Okay. All right. Thanks.
Okay. So this is what I was getting to then, that in these materials, you have a superconducting phase, and as a function of some non-thermal parameter, before you go into the normal metal, you encounter this anomalous metallic phase. And this is what I call a failed superconductor, because here the system tends to become a superconductor, but it cannot quite get there. And there's another motivation for this name, which probably, I mean, this name was given by Kapitulny, Kivilson, and al. In this review article. And I think the one more motivation to call it really a failed superconductor is because in some of these anomalous phases, people have actually tried to measure superconducting order parameter correlations. And it seems that it's non-zero. So there is a good evidence that actually the charge carriers or the current carriers in this particular phase are actually bosonic bosonic particles, and typically some fluctuating Cooper pairs and so on. But they simply cannot condense, and that's why you don't get superconductivity in this phase. So that's why this name is kind of apt in this particular case, that it's a failed superconductor. And so basically, I'm going to present a model for this failed superconductor, which is a random TJL model. So I'll get to what this TJL means. But essentially, the idea is that it's a random model and a model with all-to-all connectivity in the spirit of Sachdev-Ye-Kitaev model. So before I get to the concrete model, let me briefly motivate you why one should be interested. Why one should be interested in a random model at all. So firstly, there is always some disorder or randomness in real materials, and especially these particular materials that we are interested in, where you see this anomalous phase. So there is a good reason to consider a model already which has some randomness built in it. And most importantly, the critical anomalous phase that you see in these materials is actually present also in the presence of disorder. And it seems to not depend so much whether how clean or how dirty your sample is, at least in the set of examples or experiments that I have seen and what people have talked about. So it's kind of insensitive to how much disorder you have. And at least from the theoretical point of view, we want an analytically solvable model where we can treat disorder and interactions on an equal footing, which is kind of hard. And at least in this model, I will show you, it seems to be very naturally the case that we can treat these two things on an equal footing and in a very systematic fashion. So that's why this is an advantage. And one interesting thing is that any theory that is based on long-lived conventional quasi-particles, like in terms of Cooper pairs, or if you start from a Fermi liquid theory, then you simply cannot get this anomalous phase. And people have tried this in the past, and at least if you start with the conventional theories with conventional particles, quasi-particles, it's simply not a good enough description for these anomalous metals. So in the end, it means that you really need some kind of a theory for an incoherent metal, meaning that you need a model without quasi-particles. And the most celebrated model that we know where you get this property that you don't have any quasi-particles is the Sachdev-Ye model. So Sachdev-Ye model, just to briefly recall, is basically a Heisenberg model. But now, instead of having a particular lattice or nearest neighbor interaction, you just take some n sites and and you put spins on these n sites, and all spins interact with all of them. So it's an all-to-all interaction. And the interaction strength coupling Jij is a random number. They are all independent random variables with mean 0 and mean square value of J square.
Darshan, one question. Yeah, see, these are often very 2D materials. So is there RPS on them? Because whether there are quasi-particles or not, if there are RPS, you might be able to say that, okay, there's just no quasi-particle peak. Is there some data on any one of these materials?
Yeah, good question. No, unfortunately not. At least not that I'm aware of.
Okay.
But from what I mean, the reason why I emphasize that one needs a theory without quasi-particles is simply from let's say, a theoretical standpoint. At least the theories that I came across by reading this review and talking to people, it seems that the conventional theories simply don't give you this anomalous phase. So if you have, the conventional theories are simply too well behaved in the sense that you get a very nice Landau kind of phase transition between a metal and a superconductor.
No, that I understand, but transport is always complicated in some sense, complicated effects of some microscopics happening there. I mean, RPS would have been a direct probe of whether there are quasi-particles or not in some way. Yeah, and is there any quantum oscillation data on this? Like, have people ever seen quantum oscillations, or these things are so bad that you don't see quantum oscillations?
No, they don't see. I don't know if they haven't reported because you simply don't see it, or is it too difficult to do it? But I haven't seen any data.
Okay, take it.
Yeah. I mean, from what I understand, probably these are really difficult experiments to do. So, and very few people have been doing it. But yeah, that's a good point. But yeah, maybe people should be doing it. Okay. So I was talking about the Sachdev-Ye model, which is this random model, and you have Jij couplings, which are random and all-to-all. And this model was first solved by Subir Sachdev and Jinwoo Ye. And what they essentially showed is that if you using some fermionic parton construction and taking a large M limit, meaning you now, instead of just two flavors of spins up and down, you generalize your spin SU2 symmetry to SUM, then you can easily write down some self-energy Green's function and solve this actually analytically. And the remarkable thing was that this solution, that you have this Green's function which behaves as 1 over square root tau, where tau is the imaginary time. And why this result is significant is because this gives you a spin correlator which is 1 over tau. And this is remarkable because now if you convert this into a response function, this means that your frequency dependence of this spin correlator is simply constant, at least in the low frequency limit. And this is what the marginal behavior is. So for instance, to contrast, actually, if you would have a Fermi liquid, then this correlator would be 1 over tau square. And for, let's say, for some magnetically ordered phase, this would be some constant. So if you really have some local moments and let's say forming some spin glass or an antiferromagnet, then this would be a constant, but it is not for this particular phase, such the Ye phase. It's 1 over tau. So it's really a critical phase. And this Green's function with 1 over square root tau means that you have simply no long-lived quasi-particles. So this is a very nice solvable model, which was which has now become very famous because Kitaev and Sachdev, they extended it to now not just the spin interactions being random, but you can also consider a model with, let's say, 4 fermionic particles which are interacting, 4-point fermion interaction, which is also random and all-to-all. And in this case, there are some interesting connections to black holes and string theory, and that's why Sachdev-Ye-Kitaev model these days are extremely popular. For condensed matter, actually, there is also another reason for its interest, because all these long-standing, interesting incoherent metals or strange metal problems, they have got a new inspiration using these Sachdev-Ye-Kitaev models. And just to give you some examples of the success of using Sachdev-Ye-Kitaev type of models and its incarnations, for instance, in this particular case, we could use some similar models to explain or understand, get a model of a finite doping criticality, which is relevant for whole dope cuprates and understanding the strange metal. And in some other cases, you can also have some variations where you can, which you can use to explain certain experimental properties. Like in this particular example, this is a density fluctuation, which has been measured in an electron energy loss spectroscopy. So the first 2 plots are basically some underdoped cuprates. This is an overdoped cuprate, and the relevant plot is this optimal doped cuprate, where you see some frequency independent density correlation. And this you can, we could model using some Sachdev-Ye-Kitaev like model. And similarly, some metal insulator transitions as well, we could explain, and which fits very well with recent numerics with the Flatiron group. And there are actually many more. So here I was being selfish and just showing you the results or the models that I have studied, but there are plenty more such models that people have considered, and many such correlated physics phenomena where there have been some successful application. And this, at least it's a good theoretical motivation for us to consider this Sachdev-Ye-Kitaev like model for this particular problem of understanding these anomalous metals or field superconductors. So let me now finally tell you the model that I was talking about. So this is the model that we are interested in. So here, this is the Sachdev-Ye part, which is just the spin-spin interaction. So this was the insulating case that they considered, but now we want a metal. So we have a hopping between the electrons. So here, all the red points are basically the lattice sites, which is the number n here. And every lattice site has an electron. And you can have an electron hopping. So this is the first term, which is the Tij. And these are, again, random and independent. And then you can also have some Cooper pair hopping. This is what we consider. So one Cooper pair can hop to another place and so on. So this is why you have a KJL model. And apart from that, you have the Hubbard interaction U, and you also have the chemical potential. So as I said, these are random numbers, Tij, Jij, and Lij. And just to define the Hilbert space, it's clear that every site has 4 states now. So it can be empty, which is kind of governed by a holonic property. And you can have a single particle, whether upspin or downspin. So these are like spin-ons. Or you can have a doubly occupied state in your case.
So
and this, yeah.
Kedar had a question about how many flavors does your C fermion operator have in this?
So it's SU2 right now. So it's just, I haven't enlarged the symmetry yet. And I won't do it.
Sachdev-Ye part, you need to usually take some large M limit, right?
Right, to solve it in the Sachdev-Ye kind of trick. But I will show you another way to solve this problem. And then I will also show you how you can solve the same problem using Sachdev-Ye method. And I'll show you a correspondence between them. So right now it's SU2. I haven't enlarged the symmetry yet. I will do it in a moment, but right now, no.
Okay.
Yeah. So just to point out, in case you are familiar with the fact that usually when people study this granular superconductivity and so on, they come across this universal Hamiltonian, and this model that we have considered is actually very much similar to this universal Hamiltonian that people study for granular superconductivity. The main difference being that this T, J, and L terms are independent and random in our case. In the universal Hamiltonian, they are kind of constant.
So Darshan, one question. I mean, normally the TJ model, the Jij SI dot Sj you can decouple it into the superconducting channel and so on. In principle, you can. Why do you need an additional LIJ coupling?
Yeah, so this is motivated by the fact that we anticipate that the charge carriers are Cooper pairs, and that's why we explicitly introduce a term where you have a Cooper pair hopping already. And as I said, this also connects to these universal Hamiltonians, where people actually derived a model using some random matrix theory that you can have, that these are the universal terms that one can always have.
So is it that the Jij, if you decouple in the superconducting channel, usually gives you a D wave symmetry or something like that? It usually does not favor an S wave, at least not an on-site S wave kind of thing. So is this Lij essentially trying to give you an S wave kind of coupling, superconducting?
No. So here, this is not the effect because we are not on a lattice. So you get a D wave superconductivity if you are like on a square lattice or something like that.
Okay, you are not. You are on some random graph.
We are on an N side, some quantum dots, right? So it's a 0 + 1 dimensional system. So SI.Sj decoupling, yeah, it doesn't favor any D wave. In fact, the superconductivity here will be just doublons condensing. So like W occupied states condense and you get superconductivity.
Okay. No, because you have almost everything is both interactions and hoppings and Lij is random and all-to-all coupled.
All-to-all, yes.
Okay.
Yeah.
So I was just wondering because ultimately all-to-all coupling is not. I mean, it's a good model, but it might be. But that's not the natural. So I was just wondering whether you can make any of them not all-to-all and still survive. But maybe we can see it later.
Yeah. So that's the future goal, to come up with some lattice model. But at least at this point, I can comment that even if you consider these all-to-all models, so you can see in the approach that I will just show you in a couple of minutes that it's kind of a DMFT approximation. You can also view it like that. So you basically take a d-dimensional hypercubic lattice, let's say, where you have large number of neighbors, and you make a DMFT approximation where there is your self energy is momentum independent but frequency dependent, and you get exactly the same set of equations that I will just show you and you solve. So in a sense, there is some connection to the lattice model, but it's not that let's say very precise. It's in this large dimensional limit.
Okay.
So essentially, now the next step is very obvious, that you do some disorder averaging, and what you essentially get is a single site effective action. And this is what we want to solve. So here, essentially, you just have this free fermion part, and you have the Hubbard part, and you have the random interactions T square, J square, L square now have been averaged. And the cost is that there are these fields R, Q, and P, which have to be determined now self-consistently. And this is actually the heart of the problem of solving this, because apart from just naively solving this, you cannot assume simply any functions for this R, P, and Q. You have to satisfy this self-consistency condition that R is related to the correlator of electron, Q is related to the correlator of spins, and P is related to the Cooper pair order parameter or superconducting order parameter correlator. So before we get into actually solving this problem, just let me recall, let me make it more precise that we will be focusing at half filling. So mu is 0, meaning that you have exactly 1 electron per site. And in this particular case, we can at least roughly sketch what the phase diagram that we are expecting. So U is the Hubbard interaction. So if U is very large, then you essentially exclude double occupancy and you have a Mott insulator. Now you keep decreasing U for small positive U, you have a metal, and in between there will be some metal insulator transition. But we won't be talking about it in this talk. This was addressed somewhere else. What we are interested in is the low Hubbard interaction part. So for positive U, you have a metal, and for negative U, you have a superconductor, obviously. So this is the region that we are interested in near U equals 0. And this is where we expect an anomalous metal around U equals 0. So this is where we will be solving the model, actually. So to start the problem, to solve this problem, what we do is that these fields R, P, and Q, since we are interested in a critical phase or a critical solution, let's assume that they have some power law behavior. So this R, D, and D prime are these exponents for these fields, and there are some arbitrary number at this point, and we will put the self-consistency condition in the end once we solve this problem. So for now, it's just an assumption. We start with this power law and see where we get. So using this, what the main advantage is that we can decouple all the quartic terms by introducing some bosonic and fermionic paths. So let me just walk you through this impurity Hamiltonian. So what has happened now is that we have the coupling between the electron and some path, which is a fermionic path here. The spin operator, so this C dagger sigma C is basically spin operator coupled to some bosonic path. And the superconducting order parameter like delta is coupled to some another bosonic path. And these are essentially the free path fields. So the way to see how you get this impurity Hamiltonian is actually easy. So if you integrate the paths from this model, then you can easily see that you get back the Hamiltonian that you started with, which is this one. So once you integrate, let's say, the psi fields, you get a term which is like C dagger C. And the coefficient of it is essentially the correlator of your psi operator or the psi path. And the psi path, you can just work out from the dimensionality here, looking at the path Hamiltonian, that the correlator would be precisely this, which would have this power law 1 over tau to the power r plus 1. And this is what your R field has to be. It's the coefficient of your C dagger C term and so on. So there's nothing fancy going on here. This is very regularly what people do when solving some DMFT problems as well. You map your effective single site problems to some impurity problem by introducing some paths. And now the advantage of this is that this is a kind of a condo problem, essentially. It's a super condo problem because you have some electron which is coupled to some fermionic path, some spin coupled to some bosonic path, and another superconducting order parameter coupled to another bosonic path. So it's a complicated impurity problem, but nevertheless, it's an impurity problem which we have some experience in solving, and we can use its techniques. And this is what we will do. So essentially, once you write down this impurity problem, it's very easy to see that you can do some RG analysis in terms of small parameters, epsilon, epsilon prime, and R bar. So as I said, it's complicated, but it's doable. So instead of just one epsilon expansion for RG, you now have to deal with 3 small parameters. But nevertheless, you can do it. And what you get in the end is this kind of an RG flow. So these are the flow equations, the beta functions for this. And I'm just showing you a cut in the RG flow for G equals 0. So G is, remember, the coefficient of the coupling between the electron and the psi path, which is basically proportional to T squared. Gamma is the coupling between the spin operator and the bosonic path, and this is proportional to J squared. And V is proportional to L squared. So here, essentially, I'm looking in the flow, in the plane when G is 0 or T is 0. And you see that there is a fixed point here, which is this red point. And this I will argue later on. I'll show you that this is indeed a Bose critical metal. And okay, I mean, even at this point, you can it's easy to see because this is the fixed point where your T term is 0 and there's only hopping of the Cooper pairs. So this is like a Bose metal where the charge is carried by Cooper pair hopping. And although I'm just showing you a cut in the RG flow, you have to trust me that even if you include the other dimension, this is a stable fixed point in this G, gamma.
And Darshan, I just, so which was the Cooper pair hopping term? It was the L.
L, and which is proportional to V. So
which is proportional to V.
Yeah, yeah. Okay. So G was the T square term, gamma was the J square, and V is the L square.
Okay, okay. No, that's
so this is in the plane when T is 0. So that's why this is like a Bose metal.
Okay.
And this is stable in the third direction as well. So in total, there are 8 fixed points once you do this RG analysis, and I'm just showing you 4 of them. So there are other 4 fixed points. They are unstable, and some of them also form some fixed lines and so on, and they are fine-tuned. I'll come to that in a moment. But this is the interesting fixed point that we are interested in. And this, I will argue, is to be the Bose critical metal. So, okay, we found some basically a fixed point, which is governing the phase transition between the superconductor and the normal metal. But we should talk about it some more. What is the significance of this fixed point? So to get to that, let's look at the exponents of some physical observables. So the physical observables that we have are pretty much well defined here. It's just the electron Green's function, the spin correlator, and the superconducting order parameter correlator. And these all have some exponents like 1 over tau, eta c, eta s, and eta delta. And what this means in terms of the spectral density, which are like observables in some spectroscopic scattering experiments, is this chi double prime, which is the imaginary part of your correlators. So this basically means that it's proportional to omega power eta c minus 1, eta s minus 1, and so on. So these are the relevant observables that we are interested in. Now it turns out that actually when you do this RG, we kind of get an exact result. So even though the fixed points and the flow that I showed you is a calculation at only one loop order, this statement about the critical exponents we can actually make to all orders in our perturbative RG. And the statement is that if G star is not equal to 0, then we can exactly determine what eta c is, that is the exponent for the electron Green's function. If gamma is not 0, then we can exactly determine what the exponent for the spin correlator is, and it's epsilon. And if V is not 0, then we also know the exponent for the superconducting order parameter correlator. So this is an exact statement. But our problem is not yet fully solved, because if you remember, I just started with these fields and I assumed some power law for this field and I solved this problem. But you remember the tricky part was actually imposing this self-consistency condition. So I have to close this loop and get the self-consistency condition. And what this basically means is that in terms of self-consistency, the eta c is 2 minus 2r bar and so on. And you do some simple algebra, and the result that you get is that to all orders in epsilon, epsilon prime, and r bar, which are our small parameters, if G is not 0, then eta c is exactly 1. If gamma is not 0, then eta s is exactly 1. And if V is not 0, then eta delta is exactly 1. And what this means at the stable fixed point that I showed you, where G was actually 0, so we cannot exactly determine what eta c is at that fixed point. But since gamma and V were not 0, we know exactly the exponents for the spin correlator and the delta correlator, and they are exactly 1. And these are basically the marginal values, right? Because if you just put here 1, you see that the spin correlator imaginary part is a constant. Similarly, the chi double prime delta is also a constant. So essentially, if you would do some spectroscopic experiment, you would see a frequency independent response. And this is one of the main predictions of this theory, if this has to work out. And if people would do some spectroscopic measurements, then this is what one should see if this is the correct theory. But to date, at least I'm not aware of any spectroscopic experiments where this has been measured, but I'm looking forward to if there would be some interesting experiments on this. So this was all basically using SU2 algebra. I haven't enlarged any symmetry or anything. I've just solved the model that was given to me and did some renormalization group analysis and got these exponents and some results. What I will show you next is actually a nice way to understand how to understand this eta s equals 1 and eta delta equals 1, these marginal values. And for this, I will now demonstrate an alternative approach, which is now on the lines of the usual SYK machinery. And I will show a correspondence between the RG results and the SYK results that I will get. So in this part, basically, I have a fixed point, which I showed you to be a Bose critical metal, because this is where G is 0 and only gamma and V are non-zero, and it has this critical marginal values for the exponents. So to actually use the machinery of the SYK models, what we first do is we fractionalize. So now I'm changing gears, and now instead of just working with the electron operator, I make use of the fact that there are 4 states in my Hilbert space: the holon, the spinons, and the doublons. So here D is doublon, B is holon, and F is the spinon. And I fractionalize my electron into these quasiparticles, the smaller ones. So this is done here. And similarly, you can express your spin operator and the superconducting order parameter in terms of the B's and F's and so on. And then the idea is to obtain basically critical gapless solutions, just like the SYK states. And one more reason, or one more, let's say, perspective why you would expect now the SYK machinery to work is because, for instance, if you recall, the model was TJL model, and the T part was just bilinear in C operators. But in SYK, you have a 4 operator term, right? But as soon as now you have this fractionalization, your T piece of the Hamiltonian, the C dagger C, is also a 4 operator term in terms of these FBDs and so on. And S dot S is also a 4 operator term. Similarly, your delta dagger delta, like C up dagger C down, C up C down, is also a 4 operator term. So everything is SYK like now, and you can use the SYK machinery. So now here, to solve the problem, we now have to first generalize to large M. And now here it's not just large M, because unlike the Sachdev-Ye model, where you just had spins and you introduce some spin-ons to represent your spins, you also have other operators here. So you have holons and you have also doublons. So there are bosons as well as fermions now. So it's a mixed problem. And to consistently treat both degrees of freedom, you have to index, if you enlarge the index of your spin-ons to M, you also have to consider a general index M prime for your bosonic objects as well. So this is the label L here for the, so this is again the C operator, the electron operator. Now it has 2 index. One is the spin index and one is the orbital index. And the spin index alpha runs from 1 to M. The orbital index L runs from 1 to M prime. And this matrix J is USPM invariant tensor. So it's basically a generalization, just as you would do for SU2 to SUM, but here it's slightly more complicated. And along with this, you have a physical constraint from your Hilbert space that this F dagger F plus B dagger B, D dagger D have to satisfy this ratio M over 2. So now it's basically standard SYK stuff. It's slightly more complicated because now you have 3 particles, but essentially the idea is the same. You draw some Mellon diagrams that you would do for the SYK case. So this is the inverse Green's function for the FBD particle. You have the chemical potential and the self energy, and then the respective self energies look like this. So if you recall, if you're familiar with the SYK machinery, then these terms basically arise from these Mellon diagrams. If you're not familiar, there's nothing to worry. It doesn't depend on that. You just have to understand that you can write down the self energies for this given model and the Green's function, and you can actually solve this. So that's the beauty of this model. And once you solve this, the solution that you get is exactly SYK-like, as you would have expected. So now it's a more general solution. So the pure SY solution, the Green's function were 1 over square root of tau. Here, actually, what you get is some general exponents, some, let's say, 2 times delta. So here, the index A either could be the fermionic spin-on, the holon, or the doublon. So it can be FBD. And each of those particles have some exponent, delta F, delta B, or delta D. So this is the solution that you get for these problems. And of course, this delta F, delta B, delta D, they are not completely independent because they are all tied up because of these self energies. And then in turn, they have to enter the Green's function and they have to satisfy self-consistency conditions.
So Darshan, just one question. This constraint, when you expand the Hilbert space, you usually get a constraint. A constraint is maintained at a mean field level here?
Yes, that's right.
Okay.
Yeah. So that you can always check that the constraint is satisfied.
No, constraint at a mean field level, or you know, usually if you go beyond mean field level, if you then the constraints usually give rise to gauge theories. I mean, so that's what I was wondering.
Yeah, no. So here we are still at the mean field level. That's
so
right.
This large M allows you to essentially say the mean field is good. And
right. Yeah, that's right.
Even for the gauge fields?
Yes.
I see.
I mean, so strictly speaking, I mean, going beyond that anyways, it's extremely tough. And At least I'm not aware of.
No.
good ways
I know
to do
it's
that.
tough. I was just
Yeah.
wondering whether the large M allows you to say controllably that you don't need to.
Yes, indeed. Although we don't know how to go systematically beyond that, there have been some attempts, but yes, at least in the strictly large M limit, you can trust these results and say that this is the indeed controlled way to do it. And there are some scale invariance arguments and so on. I think Georges and Parcollet have argued for this SYK-like models. Yeah, so essentially you get SYK-like solutions, which are these power laws. And of course, these deltas are not completely independent because they have to satisfy all these saddle point equations and self-consistency conditions. So there you get a set of solutions. So it's not just one solution, you get a set of solutions. And this is what I will compare now. So on the left-hand side are basically the fixed points that you get from the RG analysis that I did for M equals 2, actually. So that's SU2 case. And this is the large M case using the SYK techniques. And here you get a different set of solutions. In the RG, you get different fixed points. So this is what we can compare now. So you don't have to worry what is FP8, FP7, or FP6. These are basically labels for different fixed points. So we can make the discussion at the qualitative level without even knowing what exactly this fixed point is. But the main thing is that what is the property of the exponents, let's say, at this fixed point. So this is where what you can focus on. So in the RG, we get a solution or a fixed point where all the exponents are marginal, is equals to 1. And this actually has a 1-to-1 correspondence to a solution that you also get from large M, where the exponents delta F, delta B, and delta D are 1/4. And this exactly gives you the same critical exponents. But the main difference is that, at least in the RG that we did for SU2, such a fixed point is unstable. The large M does say that this could be a stable critical point, but in the RG, it's an unstable. So we don't know exactly if this solution could be possible, but you never know. Maybe at very strong coupling, this could be one of the solutions.
Darshan, could you carry that index M and M prime through in the RG and explicitly see that it goes from unstable to stable?
No, unfortunately not, because we can do an RG for some arbitrary value for M and M prime. And you can write down some RG equations, but to pull it like from large M prime to M equals 2, it's not systematic. So I cannot trust what will happen in between.
No, but in the epsilon prime expansion, you can't control it?
No, because the control parameters there are completely different. They are epsilon prime, right? It's not M and M prime. So those are not the control parameters there anymore. I mean, those would have been control
in
parameters.
The epsilon prime control parameters, you can just have M and M prime as parameters in the RG equations?
Yes, we can.
And then the character of the fixed point changes when you change M and M prime?
That I have to recall again, or if I've done this explicitly. At least for the other problem, I had done this. For this problem, I'm not sure, but just from the past experience, I don't think it changes the character of the fixed point.
Okay, thank you.
But that's a good point. Yeah, that's a good point. I have to recall though what happens in this particular case, but that's a good point. Yeah, but at least I wouldn't expect some drastic change to happen. But yeah, it's worth checking. Yeah, it's a good point.
So somehow the epsilon expansion and the large M expansion are somehow taking you to different places I mean, maybe the critical exponents are same, but in terms of structure of your fixed points, I see. So you're saying they may or may not be compatible.
No, so that's the point. So there is a correspondence between the solution, but what can happen is that one of the approaches could say that this particular solution is stable, but the other could say that this is stable. But then you cannot make a final claim because the RG is strictly perturbatively and for SU2, and this is large M. So although there is a correspondence between these two solutions, and we believe this should be essentially the same solutions, but one is saying that it is unstable, but the other saying it is stable. And it could be that this, so there are different scenarios. So one scenario is that it could be that at strong coupling, this indeed becomes stable, and then this is stable even in RG and also in large M. Or the other scenario is simply there is a crossover when you enlarge your symmetry, that this is unstable only for small m's, whereas it becomes stable for large M. And this is what I think was the question, that if I do the RG for general MM prime, can I see the stability?
Okay.
But usually that's not the case. That's my experience. If it is like this RG for SU2, if you have something which is stable or unstable, usually it goes through for M and M prime, because there is no systematic corrections. At least for the other case, I remember. For here, it's a good point. I can check this. Yeah, so similarly, there's another solution where now the critical exponent for the electron Green's function and the Cooper pair hopping is 1, whereas eta s is not marginal. It's some value greater than 1. And there's a corresponding solution here, and it's actually a line of stable critical points. But the only issue with this fixed point is that it's very fine-tuned. So it happens only for certain selected values of ratio of these small parameters, meaning epsilon prime has to be exactly 4 times r bar. So it's a fine-tuned fixed point in this RG at least. Then there's the third solution that is, I find my favorite, which is the fixed point FP6 that I showed you was red in color in the RG flow. So here eta s, eta delta is 1, and this is the stable critical point. And there's a corresponding solution also at large M where eta s, eta delta is 1, and eta c is some other value. And this is indeed the critical Bose metal, because this is the solution where the fixed point flows to a value where t is 0. And so it means that you're predominantly Cooper pair hopping. The only issue with the large M in this particular case is that this is also a critical phase which is stable, but it's unstable as soon as you put some finite value of t. But that's okay, because this is still a solution at t equals 0, which is reliable, and you never know. Maybe with some large M, 1 over M corrections or something, you could have it to be stable for some small window of t as well. So essentially, this is the standpoint that we have. So we have several candidates.
So Darshan, t equal to 0 means your charges have no term in the Hamiltonian which allows them to move.
Right.
There's
Single
only
particle
pair
hopping is, only pair hopping is allowed. Yes.
Okay.
Yeah. So which is what a Bose metal would be, but then ideally we would want single particle hopping also, right? So that's why I'm said that.
And ideally, you would want single particle hopping to start with, and some of the fixed point flows it to 0, or in some way.
Exactly. And this is what is happening in the RG, right? So that's why RG gives this nice result that you start with all T, J, and L, which are non-zero, but then you flow to this fixed point, which is actually the T equals 0 fixed point. And yeah, unfortunately, in the large M, it seems that this solution is kind of strictly T equals 0. As soon as you have T not equals 0, this solution becomes unstable. But as I said, I mean, this could be an artifact of large M, and maybe with some corrections, you can actually indeed have a finite window of T where this solution is stable. So that's why this critical Bose metal is the candidate that I find is quite interesting for this anomalous phase. I mean, of course, there are other fixed points and other phases as well. There are also possible candidates. One cannot rule out, but I think this is more likely. And of course, the experimental verdict would be based on some spectroscopy and looking at the exponents. But okay, to complete the problem and to complete the story, let's also calculate the conductivity, because that was one of the key features of this phase, right? I mean, just showing that it's some Bose metal doesn't complete the story. So one also has to look at the conductivity. So in this SYK systems, actually calculating conductivity becomes kind of non-trivial. So this was derived in this paper for the TJ model, where the double occupancy is prohibited. So we used those techniques and essentially calculated the conductivity here. Now it's a bit more complicated because apart from single electron hopping, you also have Cooper pair hopping, but that just generalizes this formula. So you never mind all these small terms. The essential thing is that it depends on the spectral density of the electron operator and the spectral density of the Cooper pair operator. And NF and MB are basically Fermi and Bose function, and you can calculate this conductivity for the anomalous metal. And the main thing is, of course, the ratio between the conductivity of this anomalous and the normal metal. And we can find a bound for this. So it's definitely greater than 1, but it's also less than 2 pi. So it's not like extremely enhanced, like in some cases that has been seen in experiments, like orders of magnitude. But at least it is in line with certain experiments where it's like 3 or 4 times or 6 times the value. And in fact, this maximal value is saturated or achieved when you have this critical Bose metal phase. So there is an inequality because this depends on which critical solution that you consider, and it depends on the values T, J, and L. And if you consider T equals 0, so like the extreme case of Bose metal, then this is where you have the maximal ratio between the conductivity of the anomalous metal and the normal metal. Yeah, so this brings me to the end. So to summarize, essentially, we
just one question before you end. So this is presumably the zero temperature conductivity that
yes,
right? So is it easy to say what would be the leading order temperature dependence? Because in all those data you showed, it almost looks like a T-squared dependence.
Yeah, good point. So for these models, actually for the SYK, we know what would be the leading temperature dependence because there is this time reparameterization symmetry. And so in almost ubiquitously, it will be a T-linear term that will be the first correction. But of course, we don't know what the coefficient is, and it could be very small or very large. And then the next term is, of course, T square and other powers. But yeah, we don't know. But that's one more point that. So here we just focused on the residual resistivity. So that would be the other part of the problem, to actually nail down the temperature dependence of the resistivity and look at the solution. But I think to do that, and that's the future perspective, that one should look at some more concrete lattice model, because then you cannot rely on the large M solutions or this zero-dimensional models anymore.
But somehow having that 1 over root tau dependence of Green's functions is crucial to having all this, because otherwise you will not have any of these fixed points working out, right?
Exactly. So at least at the level of understanding, this is what our aim was, that at least we have a model, non-trivial model for the. So let me come to the summary then. That's what the point is, that we at least have a simple solvable model. Although it's kind of artificial, but at least we can look at this superconductor metal phase transition and have a theory where there is a critical phase in between at this quantum critical point, which is this anomalous metal. And at least we can show that there is some enhancement in conductivity in this space, at least in this large M spirit when we calculate. And the advantage is that we can treat disorder and interactions on almost equal footing. So there is no problem with that. And we have this critical Bose metal, which is a good candidate. And that's the future direction. So there are several things to do on this problem. One particular thing is, of course, look at some realistic lattice model. That's the main thing. The other thing is actually also look for the phase transitions now driven by magnetic field instead of interactions. So this was interactions, and now if you add another axis where you have a magnetic field, this could be interesting as well. And this is also relevant for experiments, because many experiments are done with magnetic field. And also some numerical study of this model would be interesting to put some more trust in the calculations that we have done. I mean, at least for the other random models that we did, there have been some numerics by the Flatiron group, and it seems to agree pretty well. So we are quite excited, actually, if somebody can do the numerics on this. And yeah, some other things that we have been doing and interested in is actually looking at the superconducting phase itself within this model. And that is in itself interesting, because apart from just the quantum phase transition, you can also look at the thermal phase transition from this superconductor. And now, because you have both T and J terms, so there is a competition, and depending on the strengths of T and J, you can either have a transition from a Fermi liquid to the superconductor, or a non-Fermi liquid like SYK like solution to a superconductor. So that's also some interesting perspective, like a future direction from this particular model. Yeah, thanks for your attention.
Thank you, Darshan. Thanks for this very nice talk. So open for questions. Questions from anybody, I guess. Me and Kedar asked a few questions. Vikram, any questions from your side?
I want to ask. Hello.
Maybe Vikram first and then Zahid. Yeah.
Yeah.
Okay, nice talk, Darshan. I just had a query. How important is dimensionality in the actual experimental platforms? Like, is this effect Bose metal kind of behavior seen in 3D systems also, or it's only for thin films?
Yeah, that's a good point. So as far as I know, most of these experiments have been in 2 dimensions. At least I haven't seen any reports for purely 3-dimensional system. It could be that simply this region is too small to access from the experiments, but at least technically, or looking at just the theoretical point of view, I don't see any reason that it shouldn't happen in 3D. But of course, it could be true that it could also be the case that it's really a 2-dimensional phenomena. But then what I'm also intrigued by the fact is that usually if it is really a 2-dimensional phenomenon and it's also in the presence of disorder, then at least at some point, some localization effects or some rare region effect could have played some role. But it seems that in these materials, these effects are simply negligible, or you don't see these strong 2-dimensional effects that you would have expected. So that's why
I mean, ultimately they become insulators, right? Even all these failed metals, if you, whatever parameter you are tuning, if you keep on increasing, they become insulators.
At very high, yes. But that's what I'm saying. So at some point, if the dimensionality was really important, at least this is my take. If the 2-dimensionality was really important, then at least you should have seen some hints of localization or some rare region effects, right? But it seems that at least people haven't seen it. Maybe it could be that these effects are at extremely low temperatures, even lower than the temperatures that have been accessed. You never know, but at least modulo these effects, you don't see these 2-dimensionality features anywhere. And that's why, at least this is my take, then, that it could, in principle, also be seen in 3D. But yeah, one has to think more why it hasn't been seen. Maybe there's some experimental issue.
Okay.
Zahid?
So just about the numerical study. I mean, when you mentioned that this can be also studied using numerical techniques. So which numerical technique you or typically people use to study this model reliably?
Yeah, so one is, of course, you can do exact diagonalization, but then it's a finite size problem. But people have also used DMFT. I think that's the go-to technique for all these random models and all-to-all, because there's a natural connection, as I mentioned, between using dynamical mean field theory and these kind of approaches that I just showed you, especially the RG type of thing that I was showing. It's essentially what you do in DMFT, right? You make this approximation in dynamical mean field theory that you have this model, some model, and your self-energy is just local. And this is how you map your model to some effective impurity, single site problem, and then to an effective impurity model. And this is what we also did in RG. So this is one of the very natural ways. That's why I say like doing DMFT.
Thanks.
Any other questions, comments? If not, let's thank Darshan for this very, very nice talk. And Darshan, thank you for doing it. I know it's very late at your place.
No, I'm totally fine with this. Actually, it's very quiet.
You would have to
so it's
bike
good.
back home.